Hi, today we're going to continue where we left off with ideals and quotients, picking up the last couple of examples, and then we'll talk about maximal ideals and what happens when you take a quotient by them. Okay, so we'll start with example 6 in the section in Herstein about ideals, and that's the integral quaternions. And the way these work, you'll recall that we spoke about the quaternions, which were numbers of the form, so how should I write this? So we denoted it by this fancy H for Hamilton, and we wrote it as alpha 1 plus alpha 2I plus alpha 3j plus alpha 3k, where I squared is equal to j squared is equal to k squared, which is minus 1. And we have this rule regarding ijk equals, I believe, 1. No, ijk is minus 1 as well. And that fixes the remaining relations, and we'll require alpha 1 through alpha, should be alpha 4. Alpha 1 through alpha 4 should be real numbers in our usual definition of the quaternion. So if we take alpha I in R, this is the usual quaternions. I'm going to adjust the marker a bit. Oh, maybe I'll wait till the next slide. And if we take alpha I in the integers, these will be called the integral quaternions. And we often denote this by h of z. Okay, this is the quaternion construction associated to the ring of integers. So we're going to define an ideal in here as follows. We'll let this be the ideal a1 alpha 1 plus alpha 2I plus alpha 3j plus alpha 4k, where these are all integers such that p divides alpha I for some fixed p. Okay? Then this is an ideal of the ring of integral quaternions. So I in h of z is an ideal. Okay? And if we take h of z mod I, what we'll get is the set of alpha 1 plus alpha 2I plus alpha 3j plus alpha 3k, where all of these are elements of the ring z mod pz, or really of the field z mod pz. And this is sometimes called the Hamiltonians associated to z mod pz or zp. Okay, so that's another example of an ideal in a ring of quaternions. And here, we'll recall that quaternions are non-commutative, but this is a two-sided ideal, so we're all right to take a quotient. Okay, and there's another ring of matrices, which we'll see ends up looking exactly like the complex numbers. So let's define, let R equal the set of matrices of the following form: A, and I think we take B, yeah, A, B minus B, A, where A and B are real numbers. Okay. then we're going to define a map to the complex numbers. So we'll take phi from R to C, which sends AB minus BA to A plus BI. So we have to check that this is a homomorphism. Okay, well, in a matrix ring, the addition works pretty simply. You just add each coordinate. So when we have AB minus BA plus CD minus DC, this will be A plus C, A plus C, B plus D, minus B plus D. And we have to confirm that this works when we do it in the complex realm as well. So this corresponds to A plus BI. This corresponds to C plus DI. This corresponds to A plus C plus B plus DI. So this means that the addition is indeed consistent with the homomorphism. Okay, or in other words, phi of Z plus W equals, for those two matrices, let's actually call them A plus B equals phi of A plus phi of B. Okay, and now we have to check the same is true for multiplication. So let's look at a product of matrices. So AB minus BA times CD minus DC. Okay, carrying out typical matrix multiplication, we get AC minus BD, AD plus BC, minus AD plus BC, AC minus BD. And indeed, this is of the form, so if we were to take A plus BI times C plus DI, okay, we hope that we would get AC minus BD plus AD plus BCI, because that's the matrix here. And indeed, if you do out the arithmetic, you do get that. So this implies that phi of AB equals phi of A times phi of B. Okay? So that confirms that this map phi is a homomorphism. In terms of the kernel of the homomorphism, well, in order for phi of AB minus BA to be 0, that means that A plus BI equals 0, which means that A equals B equals 0. So the kernel is just the 0, which means that this is a monomorphism. Okay? This is a monomorphism, meaning it's injective. As for surjectivity, you can easily define an inverse map. Send A plus BI to AB minus BA, so that gives us the inverse map. This tells me it's surjective, or an epimorphism. That means that this ring R is actually isomorphic as a ring, or I should say as a field, to the field of complex numbers. Okay. One last example of an ideal. If we have a ring R, let's say it's commutative, A and R, then we define the ideal generated by A to be the set of all elements of the form XA, where X is some element of the ring. Okay? So just anything multiplied by A. And you might ask, well, ideals are always the kernel of some homomorphism. So what homomorphism has this as a kernel? And it's quite simply the homomorphism sending a to 0. Okay, so if you take some so define phi from R to itself, mapping a to 0, and leaving things the same wherever else possible. Then the kernel of phi is the ideal generated by A, because if phi of A equals 0, then that means that phi of xa is going to be equal to phi of x times phi of A, so it's also going to be 0. Okay. So that's the ideal generated by A, and we'll see that all over the place. Okay, now we'll move to the next section of Herstein, where he talks about maximal ideals. And we'll start with this lemma. We saw a similar idea in the last section. What we saw there is that if R is a field, then it only has two ideals, the zero ideal and the whole field. And here we state the lemma that goes in the other direction. If R is a commutative ring with one whose only ideals are 0 and R, then R is a field. Okay, and here we can use these ideals generated by single elements to get there. So take any element A in R, okay, and consider the ideal generated by A. Ideal generated by A. So if it's equal to 0, then A was just 0. So we ignore the case where A is just 0. But the ideal generated by A otherwise, so there's only two choices. It's either 0, the 0 ideal, or it's R. Okay, once we ignore this case, that means that the ideal A is equal to the ring R. But we know that R has 1, so this means that 1 is in A. But we know A is the set of product XA where X is in R. That means that 1 has to be of this form. And that means that A inverse is equal to X. So every element, in particular, every element is invertible. Every non-zero element is invertible. Okay. And now we can define a maximal ideal. So if M in R is an ideal, such that for any ideal n satisfying M contained in N contained in R, then N must be equal to M, or N must be equal to R. Okay, so it's the biggest possible ideal until you hit the ring itself. Now let's consider what happens when you take a quotient by a maximal ideal. And we're going to claim that if M in R is a maximal ideal, then R mod M will be a field. Okay, well, how do we get there? Well, we know that for any ideal that contains M, when we map to the quotient, there's a corresponding ideal in the quotient ring. Okay? But, how should I put this? Well, let's prove this a bit more directly. Suppose yeah, so this we'll basically follow up with the correspondence theorem. Suppose n is between m and suppose n in R mod m is an ideal, then by the correspondence theorem there is n prime in R such that M is contained in n prime, which is contained in R. Okay. But we know that because M is a maximal ideal, that means that n prime has to just be M, which would mean that the quotient just gives you the zero ideal, or it equals the whole ring, which means that the quotient gives you the whole ring of R mod M. So that means we only have two choices of ideal. And this means that it is a field, by what we just saw. Okay, what about the converse? So we just showed that if M is a maximal ideal, then R mod M is a field. But what if we know that M in R, suppose M in R is an ideal, and we know that R mod M is a field, is that sufficient evidence to say that M is a maximal ideal? Okay, and the answer to that is yes. Okay, and how can we prove it? By a very similar idea. So if we take, suppose we have some n which it properly contains M and is properly contained in R, then that means that n mod M is a proper ideal of R mod M, which contradicts the idea that it's a field. So this must not be a field. Okay, this is an if and only if thing. The quotient by an ideal is a field if and only if the ideal is maximal. Okay, so let's look at some quotients by maximal ideals. The simplest one to talk about is z mod pz. So we know that the ideals of the integers are of the form nz. So we take multiples of some n. So I in z ideal must be of the form nz. In other words, the multiples of n for some fixed n. Okay? But we also know that when we quotient by nz, this is only a field when n is prime. If n is equal to ab, then a and b are zero divisors in the quotient. And that always implies that they're not invertible. Here's another example of a maximal ideal. Let's consider the Gaussian integers. And these are a subset of the complex numbers, but they're specifically complex numbers where the real part and the imaginary part are both integers. So sometimes denoted z with an I in brackets. This is the set of a plus bi where a and b are both integers, and this is a subring of the field of complex numbers. We're going to let I be the ideal, which is made up of a plus bi, complex numbers of the form a plus bi, where 3 divides both a and b. Okay. So we're going to claim that this is an ideal and it's maximal. Okay, so claim I is a maximal ideal. So let's start by proving it's an ideal. So in order to do that, we need to show it's an additive subgroup, and it has the property that whenever you multiply by anything, you get something back in the ideal. So if we take any x and y in I, we want to show that xy inverse is in the ideal. In particular, if you have x equals a plus bi and y equals c plus di, then that implies a minus c plus b minus d I should be in I. But the only condition is that these are multiples of 3, and it's easy to show that if all of these are multiples of 3, so a, b, c, d, if 3 divides all of them, then we know that 3 divides a minus c, and 3 divides b minus d. So that shows that this is an additive subgroup. Excuse me. And then we want to show that if we have x in I, and let's make it a in R, then ax is also in I. So let's show this to be the case. Okay, so x in I is of the form, oh, you know what, let's make this an R in R. So x is of the form a plus bi, where a and b are both multiples of 3, and R is of the form c plus di, where c and d are not necessarily multiples of 3. So Rx is equal to AC minus BD plus AD plus BC times I. Since A and B are both multiples of 3, this is a multiple of 3, this is a multiple of 3, this is a multiple of 3, and this is a multiple of 3, then let's just actually write this as A equals 3m and B equals 3n, so that means Rx equals 3mc minus 3nd plus 3md plus 3nc times I, which means that is equal to 3 mc minus nd plus 3 times md plus nc times I. These are obviously integers, so our x is in our ideal. So we know that I is an ideal. How do we show that this is maximal? So suppose we have some x, or rather, suppose we have some, okay, let n be an ideal such that I is properly contained in n. Okay, and we'll see what we learn about n. So that means that there must be x in n, not in I, but that means that, so x equals a plus bi, where one of those must be not a multiple of 3. Okay? Either 3 doesn't divide a, or 3 doesn't divide b. Okay. Well, let's consider a minus bi. Let's consider what happens when we multiply x by a minus bi. So that's the complex conjugate. We get a plus bi times a minus bi equals a squared plus b squared. And the complex parts cancel. And because this is a multiple of x, that means that this is in n, okay, by properties of ideals. Okay, but this is a real number. Okay, and we'll see on the next slide that this is also not a multiple of 3. Okay, so if you have a squared plus b squared, if you're interested in what this is modulo 3, okay, so let's consider what this might be mod 3. Well, let's consider what a and b could be mod 3. So a could be 0, 1, or 2, and b could be 0, 1, or 2. Now let's consider what happens when we take a squared plus b squared. So obviously here it's 0. When a squared is, when a is 1, a squared is 1. When a is 2, a squared is 2, is also 1. Okay. And b obviously is 0, and you have this symmetry along this line. When a and b are both 1, you get 2. And by the same token, since 2 squared is 1, these are also 2, and these are also 2. So for none of these besides this case, this is the only case where you get a multiple of 3 here. So mod 3, so let's make it this, let's write it this way, 0 mod 3 only if a is congruent to b, which is congruent to 0 mod 3. Okay, but since we know that's not the case, because otherwise it would be an I, this means that 3 does not divide a squared plus b squared. Okay, but when you have two integers, and they'll be positive integers, two integers that are relatively prime, that means I can combine them, so I'll have some way of writing 3t plus a squared plus b squared u equals 1. So that means that 1 is in the ideal, because the ideal has to be an additive subgroup, which means that the ideal is the entire ring. Right? Whenever you could show that 1 is in your ideal, since anything you multiply also has to be in the ideal, that gives you the entire ring. Okay, well, so we have that this is a maximal ideal, and so let's apply some of our new information about maximal ideals. We want to know what the quotient looks like, and it should be a field. So we're going to consider Z adjoin I mod I. And this is going to be just set theoretically. You can see that if you're modding out by real part divisible by 3 and complex part divisible by 3, this should look like A plus BI, where A and B are both in Z mod 3. Okay, and because this is a maximal ideal, this should be a field with 9 elements, right? Because A takes 3 values and B takes 3 values. And since they're independent, you can choose them independently. That gives you 9 values total. Okay, so we just constructed a new field we haven't seen before by taking a maximal ideal inside of a field we're familiar with. Okay, now let's look at a different ideal in the Gaussian integers. So to show I is an ideal, that I'll leave to you. It's not so hard. To show that it's maximal would be impossible because it's not actually maximal. So let's prove that that's the case. So I is not maximal because we can actually factor 5 as 2 plus I times 2 minus I. Okay. So this is when you multiply out, you get 4 plus 2I minus 2I plus 1, because plus I times minus I is positive 1, equals 5. So that means that the ideal where both real and imaginary parts are divisible by 5 is also is contained in the ideal generated by 2 plus I, right? Because multiply this by 2 minus I, you get 5. Then you multiply that by 1, you get, or multiply that by I, you get any imaginary multiple of 5I. So that means that this is in the ideal generated by 2 plus I, which is also obviously not in the this doesn't generate the whole ring. And you could show that by considering how 2 plus I times 2 minus I, or rather, would be the best way to write this. So one of the properties of the Gaussian integers, this ring, is that you can apply a norm. So the norm of 2 plus I, the size of it is given by the square root of 2 plus I times 2 minus I, which is square root of 5. And whenever I multiply by any Gaussian integer, that's going to either get larger or stay the same. So I'll never be able to make it smaller and produce a complex number, produce an inverse that gives you 1. It gives you the unit, because that has norm 1, which is smaller than the square root of 5. Okay, but that we'll discuss in more detail later. Okay. Now let's think about z adjoins square root of 2. So this will be the set of real numbers of the form a plus b root 2, where a and b are integers. Okay. And we're going to consider as an ideal here I believe it's the subset, so I will be equal to a plus b root 2 such that 5 divides a and b. Okay. And this is actually a maximal ideal. And you can prove this by arguing very similar to how we argued for multiples of 3 in the ring of Gaussian integers, except instead of looking at a squared plus b squared equals a plus bi times a minus bi, you can look at a squared minus 2b squared, which is equal to a plus b root 2 times a minus b root 2. Okay, so if you have something, suppose this is not in the ideal, you can show that a squared minus 2b squared must not be divisible by 5. Okay? It's not congruent to 0 mod 5, which means that you'll be able to construct 1. So that means that your ideal must be maximal. Okay, and when you quotient out, because clearly the quotient by this ideal has a plus b root 2, where a and b are elements of Z5. Okay, so the quotient this is a field with 25 elements. Okay, because as we said, the quotient by any maximal ideal is a field. Oops. And something you'll notice about the fields we've looked at so far is that we have prime powers as the cardinality of each of them. That's no coincidence. Okay, finally we have the continuous functions and this continuous real-valued functions on the interval 0, 1. You can show that I equals the set of functions f such that f of x equals 0 for some specific, for a fixed x. This is a maximal ideal. So if this is C01, so this is a maximal ideal in C01. And the rough idea of how to prove this is, if this is your interval, and you've got some 0 here, so if I take anything outside which isn't 0 here, I should be able to use that together with the set of functions vanishing at 0 to make the function 1. So some combination gives 1. And as we know, whenever you get the function which is identically 1, or that's the unit in this ring, because it's pointwise, it's the ring of continuous real-valued functions under pointwise addition and multiplication. So if you get the function which is 1 everywhere, then you will generate the entire ring. Okay. And you need a little bit of analysis to prove that this is a legitimate thing to do and that everything involved is continuous. Okay, so that's some examples of maximal ideals. Oh, and I should point out, what's the quotient of C on 0, 1 by this ideal? Well, that's just isomorphic to R. In particular, it's the possible values at x. Okay? So when you quotient out by, for any function you could think of, any continuous function on this interval, if you subtract off the value at x, you get some function in your maximal ideal, since that'll be a function which is 0 at x. Okay. So hopefully that gave you a nice flavor for maximal ideals and the fields that you get when you take quotients by them. And I will see you next week. Take care.